Markov semigroups on a one-mode Fock space, irreducibility and normal invariant states. So please, you have 25 minutes.
Okay, thanks for the introduction, and let me thank the organizers for letting me speak at this conference. I hope my mic is okay, so if something goes wrong, please let me know. My talk will be based on a joint work with Professor Giuliana Gredo and Franco Fagnola, which is still in preparation, should we come out really soon, hopefully. We'll be divided in 4 sections. The first one is an introduction of what I actually mean, what we actually mean for Gaussian quantum Markov semigroups. The second one should present some preliminary results and try to explain why they're called Gaussian. And then the last 2 sections will delve into the meat of the topic by trying to explain the results we obtained on invariant states and the reducibility property of the semigroup. So let me start. What is a Gaussian quantum Markov semigroup? First of all, we need to explain, well, I will just try to briefly explain what is the Hilbert space we are working on. We are working on the standard boson Fock space, which is the one mode, so it is the Fock space over the complex number, which is usually isomorphic to the square sum of both sequences with the canonical orthonormal basis, and on which on this space we have the standard annihilation and creation operators that act on the basis the annihilation by lowering the number of particles and the creation operators by raising the number of particles. And of course, these operators should be thought as unbounded operators, so should have a domain, should be considered on a certain domain, which is not the whole Hilbert space. And this will be a recurrent topic throughout the talk. We think of these, all of these operators as unbounded operators, and so we carefully think of also of their domain and not just of them as algebraic elements or algebraic items. Anyway, these operators also satisfy some nice algebraic properties, meaning on a suitable domain, the commutators is the canonical commutation relation commutator, and a dagger is the joint array. We will also need the position and momentous operators that are usually defined as sum of or difference of the A and the daggers. They also have a domain, of course. They satisfy the classical commutation rule QP equals I, and also have adjoint operators. On this space, we usually consider the observables, namely bounded operators. And as this is a conference about semigroups, what are the semigroups we consider? Of course, the evolution is given on, as I said, observables, meaning bounded operators on a Hilbert space, or morally bounded operators on Hilbert space. And the evolution is given by quantum Markov semigroup, which is, of course, a weak star continuous semigroup of completely positive identity preserving normal maps. And usually, in the case of uniform continuity of T, not just weak star continuity, then the operators as the GKSL4, meaning we can find the generator of the semigroup, and it can be written in this very well-known formula form with H the Hamiltonian self-adjoint operator and LL the Krauss or noise operators, which are also bounded. But in our intention, we want to consider polynomial that are second-order polynomial, quadratic polynomial in daggers, meaning the Hamiltonian would like to be a quadratic polynomial, and the Krauss operator would like to be first-order polynomial in any daggers. So how can we achieve this? There's a standard way to do so, and the significant ingredient is to consider the space of finite linear combination of vectors, the canonical basis. We call them psi prime and psi, and we consider the results of applying the generator to a bounded operator, which is not always possible because the generator, if we consider A and A daggers, is unbounded. So it's not always possible, but it's always possible to write this square form where all the unbounded operator now act on elements of the finite linear combination on the domain D, which I already described before. So we can give some meaning to this sesquilinear form, and with some assumptions that are actually hidden inside this theorem, when with the Hamiltonian and the cross operator we would like to consider, then we can construct a unique quantum Markov semigroup such that this sesquilinear form is actually the derivative at time 0 of the action of the semigroup on X when seen as a bounded operator on H, so that when it acts on the domain D. So after this discussion, which is actually some standard in the theory, one would say, we define what for us a Gaussian quantum Markov semigroup is, or what they are. We consider an Hamiltonian, which, as I said, is a second-order polynomial in A daggers, and we choose the parameters that appears in its definition, such that H is a self-adjoint operator. And the cross operators here are just first-order polynomial in A and A daggers. One note should be that the number of cross operators we are considering is 2 at maximum. This is actually trivial in some sense because a third operator would just be a linear combination of the previous 2 cross operators, meaning we can always, because A and A daggers are linear independent and form a basis in some sense of the polynomials. And but this will be relevant in the following. We just have to consider 2 cross operators because a third would be just linearly dependent from the previous 2. Anyway, if we consider the semigroup, the quantum Markov semigroup coming from this particular choice of operator H and LL, then this is a Gaussian quantum Markov semigroups. And all the Gaussian quantum Markov semigroups are those arising in such a manner in our definition. Okay, so now that we've introduced them, why are they called Gaussian? And in order to answer this question, let me first look at what is the quantum characteristic function. So something that is related with states. We consider normal states, so density states that have their density matrix, which is of course a trace class operator. And the quantum characteristic function is defined for all complex number by this expression rho hat, which is the trace of rho against an operator. For you that do know this operator, this is a Weil operator. But for now, let me just remark that this expression should morally correspond to one thinking that this formula is actually evaluating a sort of classical expectation over some state of a random variable. Here, we do not have a random variable, we just have a Weil operator, which is a unitary operator, and can be defined and extended via these exponentials, which are linear in a dagger, or using the definition of a momentum and position operator as linear combination of P and Q. And this particular last expression is relevant because now, again, morally thinking of the quantum characteristic function as a classical expectation, then this exponent corresponds to the expedition of this quantity, which is actually a classical quantum characteristic function of a random vector, where the random variable here are minus square root of 2p and square root of 2q. So the next step should be, can we ask for the quantum characteristic function to have a classical expression, meaning to be the classical characteristic function of some random variable? Well, we can, not as easily. There are some theorems behind this, but we can define rho as a Gaussian state if its quantum characteristic function is the characteristic function of a normal random vector, a bivariate normal random vector. And here I've written this statement in a compact form, meaning that in the exponential there are omega, which is which is the complex number, but should be thought as the mean vector, and S, which is the covariance operator, is a real linear operator from C to C. But when one could recover the usual expression for the classical characteristic function by just thinking of Z as not as a complex number, but as a pair of real number, namely Z equals X plus IY. And in this way, we recover the classical expression where omega translates easily in a vector, in a mean vector, while S, that once was an invertible real linear operator, now becomes a matrix in some sense, a linear operator from R2 to R2, which is represented as a matrix. And it's not clearly visible in this, with this font, but S here is written as a boldface character, meaning to differentiate it from its real linear counterpart, but they actually are the same operator morally, just one acts from C to C, the other acts from R2 to R2. Okay, now that we have Gaussian states, we can actually define why these are called Gaussian semigroups. And the reason is this theorem, which is, we say essentially that this semigroup preserves Gaussianity, meaning that if we start from a Gaussian state, then its evolution under the Perdue semigroup is still a Gaussian state, whose mean vector and covariance operator are given by these formulas, where again, Z and C are real linear operators. And we can write this whole page as operators, linear operators from R2 to R2, but for compactness, we use real linear operators, which are one-dimensional. And another nice result that actually leads to this should be gone first, then this result. But I will present you now is we can find explicit action of the semigroup on Weyl operators, and this results in another Weyl operator multiplied by a constant. And actually, to achieve this result, now that I see that Professor Teretenkov has introduced me, actually to achieve the result, we performed some calculation, of course, with the some algebraic calculation, what we say, with the generator, in order to prove that actually this action on the Weyl operators coincides as the same expression of the form of the generator when considered as in our definition. And the calculation we've done are really similar to what Professor Teretenkov has made on his article on Idacopy of the last year, I think. Anyway, this is a well-known formula. Actually, is often seen in the literature to introduce Gaussian state, or how they are also called quasi-free, not Gaussian states, but Gaussian quantum Markov semigroups, or as they are also called quasi-free quantum Markov semigroup. And actually, there's a result we are working on, which is sort of known in the literature, but bits and pieces are separating into different papers, and probably there are some gaps that needs to be filled, but we are trying to do that in order to hopefully prove the theorem that actually a QMS that preserves the set of Gaussian states needs to act on the Weyl operators in such a manner. So this theorem is usually known, but actually is also necessary in order to preserve the Gaussian states, and so in also to speak about Gaussian quantum Markov semigroups in some sense, in the sense we have given. This is the first motivation for why these semigroups are called Gaussian, but we can give another motivation when looking at the first important topic about my talk, which are invariant state. The first, well, a new topic of invariant states in some sense. Of course, invariant states are states that are invariant under the evolution of the Perdue semigroup. And the main result on invariant states is that a Gaussian semigroup as a normal invariant state, if and only if its parameters lie in the region I, which is the region I will show you in the next slide. But for now, we just note that we can say when a Gaussian semigroup has a normal invariant state. by just looking at its parameters. In the case, moreover, the invariant state is Gaussian and it is unique. So this semigroup, when it has an invariant state, it has a Gaussian invariant state, a unique Gaussian invariant state. And moreover, we can find an expression, a formula for its parameters, omega and s. Down below, I just recall you what were the definition for the Hamiltonian and the cross operator, meaning you can sort of look at the formulas, understand where things play a role. And gamma here, which is a new parameter that appears in the description, will be relevant also when talking about the region I of the existence of a normal invariant state. So let me change the slide to look at this region I. The region I of the existence of invariant state is the shaded one, the gray one, and gamma that has the role of measuring how much the A's prevail on the daggers. For invariant state to exist needs to be positive. All the shaded region is on the right of the y-axis. Moreover, the other quantity gamma squared minus modulus kappa squared, it doesn't really matter when it's positive, but when it's negative, it adds some stronger requirements to gamma, implying that it should be even more positive than this. Actually, this result can be nice, but also quite obscure, but actually can be motivated rather easily, and that's what I would like to do in the next slide. Of course, the result itself comes from many different results, and it comes from many different pieces. But to understand, just to get some intuition why this is true, I hope the next slide will be sufficient, where we look actually not an invariant state in general, but a Gaussian invariant state. If a Gaussian invariant state to be invariant, then of course its covariance operator should be invariant under the evolution, and we have an expression for the evolution of the covariance operator. We can then exploit this condition in order to obtain this integral equation. And one can actually observe that the operator S, which is defined as this integral, and is actually the form of the invariant covariance operator, which is given in the theorem before. But anyway, one could look at this operator and observe that it is a solution of this equation, and that actually nullifies the operator in the brackets of the integral. Of course, if it exists. So if it exists, this operator solves the equation above, and so it should be the covariance operator of a invariant Gaussian state. And this operator exists in for example, when Z is stable. So when Z has all the eigenvalues of Z have negative real part, and Z is then a matrix given by this in this form. Its eigenvalues are given by these expressions, and one can see that actually the requirement for these eigenvalues to have negative real part really coincide with the requirement we made for the parameters to lie in region I. So actually the region I is just the reason when the matrix Z is stable, so the region when we can find a Gaussian invariant state, which is given by the formula we provided in the theorem. Of course, they're still missing the pieces that outside this region, there are no invariant state, and that's something we dealt with in the paper, but I will not show you today. Another piece that is missing from the proof is that, okay, we have a Gaussian invariant state, but can there be any other invariant state? And to answer the question, one thinks that really is really helpful is to look at irreducibility. And that's the other main part we looked at when dealing with these semigroups. And irreducibility is defined by this implication, meaning that if we have a projection that increases under the evolution, then it should really be either the zero projection or identity projection. Meaning irreducibility means just that we cannot find a subspace of the system where the dynamics can be reduced. You have to think of this semigroup as a whole, and you cannot just study it on some subspace. And the main result on irreducibility, it just comes from this decision tree, meaning that you can follow the decision tree, you can answer these two questions, and you find out whether your Gaussian semigroup is irreducible or not. Again, these results is really compact, really nice, but where does this come from? Again, we can provide some intuition on why this is true, and what to do in order to do so. One actually has to really discard all the consideration one has to do on domains, because the consideration on domains and technical consideration are really what sets this problem apart as being really difficult. You have to be careful when dealing with these operators. But if one just focuses on the algebraic part of the result, then it should be easy to get an intuition of why this result is true. So it all boils down to this result of Fagnola-Arboleda, which means that a projection is called subharmonic, then that is increases during evolution. We can shift the attention, we can shift the solution of this problem to a problem on operators that appear in the generator, meaning that if a projection is subharmonic, then its range should be invariant not only for the Krauss operators, but also for the contraction semigroup generated by G, where G is just an operator depending on operators of the generator. So again, there are some really technical parts regarding the domains. One should be really careful when doing these calculations. But if one just focuses himself on the algebraic condition, then the second condition one has is that for a projection to be subharmonic, its range should be invariant for the Krauss operators. And this means, and if we have two linear independent Krauss operators, then we can find, write both A and A dagger as linear combination of said Krauss operators. And so a candidate invariant subspace should be invariant also for A and A dagger, and this is not possible. So with this simple consideration, which I have just explained, the first question one asks himself: if you have two Krauss operators, then the semigroup is irreducible, because you cannot be irreducible, you cannot be invariant for both A and A dagger. But if you're just one semigroup, then we need to consider another quantity. Where does this quantity come from? It comes from the requirement that a candidate invariant subspace should be invariant for both L and the generator G, because if it is invariant for the whole semigroup, then it is invariant for the generator. And then if it is invariant from G and from L, it should be invariant from the commutator. Again, all these things I'm saying are just independent of domain problems that should be addressed, actually. But if we disregard for a moment the domain problems, then the commutator of G and L has the expression where, again, it appears an L, it appears an identity operator that clearly leave a candidate invariant subspace invariant. But a new term that I've written in blue appears, and this is a linear operator in A daggers, and we can consider it actually as an L tilde, or as a new Krauss operator in some sense, because a candidate invariant subspace should also be invariant for this operator L tilde. And if so happens that L and L tilde are independent, then we are in the same case as before, where a candidate invariant subspace should be invariant for both A and dagger, and so leads to an irreducible semigroup. Condition for linear independence is easily written as this determinant being different from 0, and so this should also explain at least why, if this determinant is different from 0, the semigroup is irreducible. Clearly, there are lots of other things that needs to be addressed in order to properly solve all the irreducibility problem, but this is the intuition I would have liked to give you, and this concludes my talk. So thanks for your attention.
So thank you very much. Any questions or comments? Well, Maybe I will ask a question. So once again, the result is following the situation when we have, as you said, stable matrix. We have the invariant states.
Yeah, exactly, and they are the only case in which we have an invariant state. That's also the point.
When stable, we say strictly positive, or I mean, it's strictly stable, or it's possibility of zero real parts of eigenvalues. So I don't understand this region.
Okay, the region, this region I'm describing here is just the region where the eigenvalue have strictly negative real part, strictly negative. So because in this discussion, I just would like to give an explanation, an easy way of where this integral exists. Of course, as you said, we can find some possible relation between Z and C such that this integral exists even if the matrix Z has eigenvalues with zero real part. We addressed this question in our paper. We tried to, of course, consider the case when Z could have zero part eigenvalue, but they will be nullified by C in some sense. But in that case, an invariant state does not exist. So this is just was just an easy way to.
So the invariant state, it means it's preserved by evolution, or it's stable. I mean, or it's stabilized by evolution. I mean, we have at infinite time this state. It is.
Actually, in this case, I would say they sort of coincide. I don't know whether in the case where it's probably sort of coincide, because here invariant state is just defined by a state which is left invariant under the evolution of the Markov semigroup. We also proved that in the case a normal invariant state exists, then there's convergence to it in the evolution, starting with general invariant state.
Because I understand the convergence to the state when we have strictly negative eigenvalues, but if, for example, if we have no dissipator at all, if we just unitary dynamics and some invariant Gaussian state with respect to unitary dynamics, as I understand it is invariant state in your discussion. I don't understand this small part of the story.
Okay, we are not considering actually a part where there's no dissipator.
Okay.
So we ask for at least one cross operator. So the cases we are considering are either there's one cross operator, there's two cross operator. I don't know if I can ask you if I can answer your question when there's no invariant state. I mean, I cannot. I don't know if I can answer your question when we have no normal invariant state and we just look for asymptotic convergence of an initial state. I cannot answer your question in this case, but in the case that there is a normal invariant state, then any initial state converges to the Gaussian invariant state at least weakly, like in the zero means limit.
I see. Thank you very much. Any other questions or comments?
Maybe I have a question. Can you hear me?
Yeah, I can.
Okay. Can you distinguish the parameters that correspond for invariant state that correspond with the Gibbs state? You know the Gibbs state. Is it possible to distinguish the parameters that correspond with this state?
Oh, well, I mean, this should be easily seen when with a process of sort of diagonalization of the matrix. But in this formulation, As far as I know, you cannot distinguish easily the Gibbs state here. I mean, if you can sort of diagonalize the invariant state, then you can find by a Bogoliv transformation, you can find actually some that the Gaussian state is really a Gibbs state e to the number operator in some sense, with some transformation. But
and the Gibbs is a good candidate to be invariant.
Yeah, in some sense, all Gaussian states are sort of exponentiation of the number operator. You just have to sort of diagonalize the covariance matrix as you do in classical or normal random variable. You have some Gaussian somewhere, and you can diagonalize it and see as two independent Gaussians. And in some sense, here again, also you can see a Gaussian state as e to the number operator in some sense. But when you mix the Gaussians from with one another, then it's not so clean. It's not really e to the number of operators, e to the some quadratic polynomial, let's say. Yeah, and to really focus on the Gibbs state, you should diagonalize the, in some sense, the covariance matrix. Yeah, if that answers your question, I don't know if I.
Thank you.
You're welcome.
So, any other questions or comments?
Just a quick question. In your theorem, you have this quantity S, this integral. Could you remind me what the matrix C in the middle is?
Yeah, of course. Well, it's not really so clear what, I mean, at least for me, what the matrix C is, but the matrix C corresponds to this real linear operator. And I don't know if you're familiar with converting from real linear operators to matrices. But actually, this correspond to 2x2 matrix of the diagonal part are the imaginary part of this value VL UL, while the diagonal part are some let's say absolute values of UL plus VL.
It's just that your integral S reminds me very much of what are known as Gramians. These arise in, for instance, linear systems theory, where you want to discuss observability or controllability in the Kalman decomposition.
Yeah, I don't know if they're the same thing I'm thinking of, but maybe they remind you that because they actually come from the solution of this equation, which is usually seen in control.
Yes.
Yeah, exactly. We can actually see that Gaussian invariant state as unique solution because this solution that has been analyzed several times in control theory can be written.
It's very reminiscent of Lyapunov type results for
exactly. That is where they come from.
Linear systems, yeah. Again, with the Kalman decomposition, you get some nice results coming out about minimality as well.
Sorry,
minimal realization. How many oscillators do you actually?
Okay.
Yeah. These are the type of things engineers worry about. But yeah, I suspected there was, but yeah. Okay, thanks very much.
All right, thank you.
Well, okay, let's thank the speaker.